Morning. My name is Fiona Williams. I come from Ireland, originally from Dublin, the main city in Ireland, and I've been living here since 1991 when I moved from Ireland when Ericsson was setting up its operations in Germany, and I moved to Germany to set up the research department at the time for Ericsson, and I've stayed since, so I've been here a long time. I'm a native English speaker, so if I'm speaking too quickly and you can't understand me, just signal and I'll slow down because I tend to talk quite quickly. Okay, I'll move to then my presentation. I want to talk about ICT for smart energy. In particular, I'm going to talk about 5G. And I want to give you an overview, more or less. What's driving the use of 5G and ICT in the smart energy area? What are the new technologies that we're working on in Ericsson together with the energy sector? So we're working on various energy technologies and how they interrelate to 5G. And I want to explain that to you in several projects. Then I'll go into 5G, a bit about the characteristics of 5G and a couple of the features. I won't have time in the presentation to go into all of the details, but my colleague Stefan Bretzke, who speaks after me, will go into a bit more depth. And at the end of my presentation, you'll see a few references to white papers where you could start to find out more if you're interested to learn about 5G. There's a lot of material available online. But what I want to try to give you is the material that isn't available online. How do things fit together? Why do we do it? And then I'll finish with a couple of slides on laboratory testing and field trials that we're running for several projects. So why do it? Most of you will probably remember in 2016, the storm Ophelia. At least those of us who lived in the countries affected by storm Ophelia will remember. At the time, I was in Ireland in the week before the storm was due to come. And in Ireland, it was the biggest storm in living memory that was expected to come across the Atlantic. And it was very unusual because it was one of 10 storms that recently before that had made it across the Atlantic, and that was very unusual. And in Ireland, all of the public transport was closed down in advance, all schools were closed, all public sector buildings were closed, everything was closed. And I grew up in Ireland. I've never seen that before. It never happened before. So it was enormous. And it brought down a lot of power lines. You can see one here in Ireland because the population is very spread out. Apart from Dublin, you have overhead power lines. You only have underground power lines in the cities and major towns. So there were huge problems. This map shows the clusters of outages, not the individual outages, the clusters of outages. Most of the country was without power because of so many individual faults in the system. And it took over a week to reconnect some of the houses and customers in this part of the country. So it really took a long time. There were enormous storms and dangerous situations with wires on the road. And this is becoming much more common. The storms are continuing and the storms are more severe than they used to be, which means that the power supplier has increasing problems. The time between storms is too short to repair the network. The next storm is there, bringing down more lines. And that's becoming a really big problem for ESB, which is a dominant power provider in Ireland in the distribution network. And they're investing in more automation in the network so that they can reconnect the customers more quickly. And recently, the regulatory regime was changed. So in Ireland, the power providers have to pay a penalty for the lost minutes of customer service. So if you have a power outage, the minutes are counted and the power provider pays a fine to the government for every minute of service lost to the customers. And that amount, the amount of fines is growing rapidly because of the storms and their severity. And the business case then to invest in new technology to reduce the number of lost minutes by reconnecting people more quickly, that's very positive. So there's a great deal of interest from the power provider in Ireland, the same in Romania and Italy, where penalties have also been introduced. they're very interested to invest in distribution automation, even without other regulatory changes. So these are big drivers. Another issue is that the climate, it's not just getting, we don't just have more storms, we have less rain, so we have more droughts and very hot summers like last year, and shortages of water are becoming common. And increasingly, the water network tends to look like the power network. You have the same smart meters, and you have less water, so you have to pump water from one place to another in order to have a reasonable supply. And even in Scotland, where if you've been to Scotland in the north of England, it rains a lot, even more than in Ireland. And in Scotland, they have water shortages because of the drier climate and much less rainfall. And that means pumping water all over Europe to have a reasonable supply. And those pumps have digital interfaces, which have exactly the same threats and vulnerabilities that the meters do in the power system, and you have the same type of actuators. Then you have cascading effects. When the power goes down, the water is out in many countries. Before, it was gravity flow for water, and you didn't need to have power in order to have a water supply. But the more you have to pump the water, the more reliant you are on power to have a water supply. And in Germany, the water is pumped everywhere. So if there's no power, there'll be no water. And the shortage of water will be more quickly a problem than the shortage of power. So there are big social issues regarding critical infrastructures and increasing reliance on the power supplies. And this is driving change and the move to ICT. Another issue related to climate change is the need to reduce CO2 emissions and changes in the regulatory framework to open up the markets and make them more efficient. So you have lots of new sector actors like virtual power plant operators, service providers, aggregators at all levels, and microgrid operators. You've got, at the same time, more volatile renewable energy source generation and less synchronous generation in the network, more prosumers, more energy storage, more sector actors, more digital interfaces, and new business models. And all of that change is driving the introduction of ICT, because you no longer can count the number of energy generators on two hands, as was previously the case in many countries. You had a few power stations and that was it. Now you have prosumers generating power, and in order to manage such a situation, you have to have digital interfaces, and we will need electronic markets for power on a much larger scale in the future. So that's driving change in the sector. And then I mentioned security and the vulnerability of digital interfaces. And this is something which is new in the energy sector. The more digital interfaces you introduce, the more new vulnerabilities you have. And in Ukraine in 2015 was the first known successful cyber attack on a power grid, the first publicly announced one. And it brought down large parts of the country. It was it took over 6 months to plan. Initially, people were on a course. They got a USB stick with the course material, which they, when they were on the course, used to upload the slides to their PCs. They brought their PCs back to the power utility where they worked, and through the interface of having downloaded the slides for the course, malware got into their system, which spent months learning how the system was configured, and then eventually got passwords from administrators, and it was quietly over months feeding all this information back to the people organizing the attack, who had then the choice of when they wanted to actually launch the attack, and they eventually launched it and brought down large parts of the network, and it took over 2 years to work out how they had made the attack. So it's a quite complicated situation. It wasn't one person working in their bedroom bringing down the whole network. It was a very well organized attack. And then you have accidental blackouts like the one in 2006 over much of Europe, where a line was to be switched off for the launch of a new ship, overhead line over a port, and it was thought safer to switch it off. It had been planned months in advance. It was to happen on the 4th of November, which was Friday evening, if I remember the details correctly. And then shortly before the date, 3 days before, the ship producer asked if they could change the date by 1 day and move it to the Saturday. And everything had been planned and simulations had been run for the power grid for the original date, and they thought moving it 1 day, it's a Saturday, maybe it'll be more easier to run for the power suppliers. So they said yes. But the power operator who was organizing it in northern Germany was quite slow to tell all the other TSOs. And then it turned out that on the next evening, all the other TSOs had already sold the capacity of their networks to balance power. And then the situation was much more critical than originally planned. And the simulations hadn't been done in that context. They'd been done in a different context of everything being planned for the night before. And when they eventually switched off the line, the effects weren't the ones they thought, and their first actions made the situation worse and brought down more power providers. So it's not just attacks that are bringing down the power networks, it can also be the complexity of the networks and the fact that what used to be an easy situation to manage because there was lots of capacity available, it's now very difficult because all that capacity is being sold on various energy markets. And that means there's very little reserve to do anything if something happens. So the situation has changed. The complexity of the situations is orders of magnitude different than it used to be, and the social effects, because water is also affected and public transport and everything else that now relies on power. Increasingly, the whole of society is relying on power. The effects of power outages are much bigger. So this is driving the need for new technology and new digital interfaces, and they all need communications generally. So we have more solar power. You can see solar power growth on the upper left, in the lower left, and wind power growth on the upper left. It's increasing in the volume of production, whereas at the same time the production of power from coal and nuclear is decreasing, and it used to bring, and still does bring, the synchronous generation to the power grid, and the inertia is used from the synchronous generation to stabilize the frequency, and that's increasingly missing as you move to renewable sources of power. So we've been looking at how to manage this situation of greatly increasing levels of renewable energy in the power grid without synchronous generation in the RESERVE project, and we've looked at both techniques for frequency and for voltage, which you'll have heard about in other presentations. I'll just say for frequency and voltage, we've also investigated the scenarios from the perspective of the full-scale rollout of the technique to be used. So if you were to take the techniques being developed in the energy research area and apply them to a whole power grid, what would the architecture of the ICT look like? That was what we looked at. So we looked at different architectures, centralized, decentralized, and distributed. And we looked at what would be the requirements on the ICT and the requirements on the 5G networks if you were using 5G instead of wired or fixed or fiber communications. What would the requirements be? Because we wanted to see what the latencies were and whether 5G could fulfill the requirements. And we made various tables. You can see them here with different latencies for different types of configurations. And it gave us a good feeling for what we needed to do. And we had up to 5 seconds, I think up to 30 seconds is the highest figure there, to organize the communications, and up to 1 second in the worst case. So we need a fairly low latency network. 1 second you couldn't manage with 4G LTE wireless systems at present. You can do it with 5G, but not with the general public. 5G, which will be introduced to the market immediately. You can do it all right with 5G private networks if you configure them for the particular case. There are many demonstrations of 5G with latency under one second, in fact far lower. So it's coming, but not quite there. So it's a challenging use case for 5G to look at frequency control. In voltage, we did the same thing. We looked at the full-scale rollout of hybrid network techniques, and we looked at the various architectures you could use, and then what would the general implications be. And whilst the latency was generally not an issue for the communications, when you want to synchronize the voltage or give new work points within the system, it has to be done within a quite short period of time. And the initial estimate was 200 milliseconds to do the calculations, to collect all the information and give new data back to the power equipment and the inverters. And that's quite challenging, actually, to do with wireless communications. So even in voltage scenarios, we found some interesting aspects. A further aspect is that in both of these scenarios, you need to connect a lot of new endpoints. So you've got lots of devices and sensors that you want to connect to, and it becomes very expensive if you want to deploy fiber or cabled connections to all those points. And then you would immediately look at a wireless network, and then you want to know what the reliability is and the latency and the characteristics of the network. And that was one of the reasons 5G is developed specifically for such industrial automation problems. The reliability and availability were key issues in the design of 5G networks. Further point, I've mentioned blackouts have enormous consequences for society, and they're growing all the time. So we've been looking in other projects, such as the eSafeNet project, for techniques that would make the recovery from blackouts easier using microgrids. And if you have no power, typically you have no communications, unless you've organized that the power network has battery backup and diesel generators, or can get power from somewhere outside the blackout area. And these cases it's not so difficult to organize that you have battery backup for your base stations and for the core network that you need to run wireless communications, but it's expensive. So normally public operators of wireless networks don't have more than half an hour of battery backup, if they even have that. It's too expensive to even do that for most normal public communications. So for the power networks, you have to organize it specially. And what you have to know from the power network perspective, if you're using wireless communications, is that you need power at the base station, so the antennas that you see on the roofs. And you also need power in all the servers, which are called the nodes of the core network that make the base stations work. And they can be very far distant from the base stations. They can be hundreds of kilometers away. They can even be in a neighboring country. So you need power at all the locations for the wireless communications, public wireless communications to work. You can get around those problems if you have a private network and you put to the core network right at the base station and you have a battery backup or diesel generator. Then you can have a self-contained system, and that's increasingly the trend. In 4G current LTE systems, such systems are becoming popular as private LTE networks, and the same for 5G. In fact, in Germany, spectrum is allocated in Germany for industrial automation so that large industrial companies or sectors can have private networks with just serving them and their requirements and organized to suit their configurations. But this was one technique we worked out in eSafeNet. We looked at the situation of after a blackout, bringing up microgrids using mobile communications. We have, after a blackout, the plan to organize 2 microgrids. You have a power outage in the main grid. You can see the 2 base stations. And after the power blackout, the mobile communications kicks in and organizes the microgrid, which can then be used to reduce the effects of the outage and bring up the power network more quickly. Then I mentioned security. We've also been looking at techniques to improve the security and to analyze the security of power networks. Starting from the data collection, we've been working in a project called Success on real-time secure smart meters. We've been working on the communications to those meters. We've looked at the threat and analysis aspects of detecting that attacks have happened. And we've been experimenting with blockchain-oriented security on top of the encryption of the meters to detect if the encryption's been broken. And that's increasingly being used, that you have, because many or often it's not clear that an attack has happened until many months afterwards. If the software malware is downloaded to the system or the encryption has been broken, it's then up to the attacker to decide when to launch the actual attack, but the utility may not be aware that their encryption has been broken. So we've been looking at these aspects. How can you detect attacks? And not just at the DSO level, but how can you detect attacks which might look like small-scale attacks from the perspective of each individual DSO, but if they're happening at the same time in many countries or many regions, it could be a planned large-scale attack. And in order to experiment with this situation, we developed a large-scale monitoring system, which we called a pan-European monitoring attack monitoring system. We've built a prototype and demonstrated it with 3 DSOs in Europe, supplying data on simulated attacks in their network to show the effect and to show the type of data overview and representation of such attacks that you could have. And that fits quite well with changes in the legislation in Europe, the NIST regulation, to move towards increasing electronic reporting of attacks on critical infrastructure and to make them visible at above the DSO level, between the DSOs, at the regional level or at the national level or at the European or international level. So we've been experimenting with that. And then we've applied all of the countermeasures in trials. This is just a slide on the European level monitoring system. We have it connected to, here in the diagram, 3 DSOs. You can have any number of DSOs. Each of them has a module, the DSMIS, which connects to the monitoring system. And then you can interface to all the DSOs systems and you get an overview of what's happening in small but similar attacks that might not be recognized because that's seen as a growing threat. Then to the final project I mentioned and the final set of technology that's being introduced that we've been working on. It's the Sonio project, which is working on the vision of automation as a cloud service. And here the context is that you have generation, you have cloud-based automation services, which are supported by AI-based systems, self-learning systems. And the idea is that you can connect sensors and actuators in the power network with 5G, and you can use them, you can use the services which are then based in the cloud for remote control of the network, for load forecasting, for FLISR, self-healing applications, for power quality evaluation. And the service provider always has the latest software because the software is in the cloud and not loaded on the individual devices. And that's usually a big problem to update the software on the individual devices in the power network because they don't have the type of download systems that you have on a mobile phone where your software can be securely downloaded and you know the software you get is that which was sent and it works automatically in the background. That's not commonly used in the power network and it can take months, if not years, to update the software on individual devices. So this way of organizing things where all the software is in the cloud gives the flexibility to the DSO that they always know they have the latest version of the software. The systems to deploy software to devices can be those of a mobile network. The same systems can be used in such organization. And it also means that the software is maintained by experts who are supporting a large number of DSOs. Could be a large number of small DSOs. And many of the smaller DSOs have very small or no IT departments and very little expertise on all the different networks they could use. So this type of organization of distribution, automation of distribution networks has a lot of advantages for smaller DSOs. And I think it's going to be increasingly the trend. It requires some regulatory change to enable the DSOs to offset the cost of the investment against the price of electricity. But this regulatory change, which we've been lobbying for in the Sonio project, is included in the winter package published recently. So the trend is in that direction. And even without that regulatory change, the introduction of penalties means that this type of technology is very attractive already for the operators in countries that have penalties, because it enables them to reconnect the customers more quickly, and we're running trials of this. So I've mentioned the services that Sonio can enable in the cloud, and it's based on 5G devices and high levels of renewable energy sources in the network. So to summarize, commercial utility networks increasingly require very high availability and reliability, secure communications to many new endpoints, latency at near real-time levels, service provider control of quality of service and security, support for highly distributed power network architectures, and automation as a service in the cloud, and flexibility to adapt as the circumstances change. So moving on to 5G, you might wonder where the G's come from. If you were a user of GSM systems, or even before it, 1G systems, which were analog-based communications, you might have noticed that every 10 years approximately a new system comes on the market. And that's because the spectrum which is used by the systems is allocated globally once every 10 years. And that makes the introduction synchronized globally, because these days you want your mobile phone to work all around the world. In previous generations it didn't. For example, in third generation you needed different phones for Asia than for Europe and the USA, but in fourth generation, the current systems, one phone will work everywhere. And that's because of this global standardization of the spectrum and the global standardization of the interfaces of the system. And it has many advantages. It also has advantages because the encryption used in the systems is developed and tested by a very large number of people. And the security and encryption of 4G systems has never been broken. And now we're on 5G. So the security that you get by developing in such a way is very high, and the reliability of the systems, because they are being implemented by different manufacturers all over the world on an enormous scale, it also brings down the price. There's no way to produce a cheaper system than a globally standardized one, because it's produced in such volume that brings down the price of the communications of the equipment. The equipment is produced in enormous volumes. So now we're at 5G, which is being introduced on the market this year, and we've had prototypes for the last few years available for use in our laboratory trials. But first, installations of the real network are being installed this year in various countries, and it will be in many major cities next year, and the following year the rollout will really gather scale, but in many cities it will be introduced on a large scale end of this year, early next year. I mentioned already that 5G was designed for industrial automation, in particular for critical IoT devices, where you need very high reliability and highly available systems, for traffic safety and control of traffic lights, etc., or self-driving cars, remote manufacturing for fleet management, and massive IoT, smart meters, tracking, etc. But the most difficult requirements we have to meet are in the industrial automation, critical IoT sector, and the requirements of the utilities and power networks come in this area, and they're very similar to the requirements of manufacturing, as you don't want robots to knock people down or injure people or have other problems, and they require very low latency and very high reliability. So you find that those cases. Then you have fixed wireless access as a major part. Throughout the world, wireless is being used to provide people with internet access, and 5G will give them high bandwidth internet access with a wireless connection. It's already been rolled out in the US, who are very interested in that. And enhanced mobile broadband is aimed at consumers and mobile operators. It gives you more bandwidth. It makes everything faster. And that's the first use case that's being introduced on the market in most countries for 5G, because everybody wants faster internet over their mobile phone, and the demand is enormous to increase the bandwidth availability. So what's happening is that we're rolling out to new base stations and antennas, so just the wireless end of the network, but not the core nodes. the wireless part is being upgraded first because that gives the advantage of increased bandwidth to everybody, but it doesn't have the lowest latency and the full spectrum of functions which will come when all the nodes of the core network are replaced. So the system with the new base stations and the LTE-based core network is called non-standalone 5G, and that's what's now being introduced. And in a couple of years' time, the new core network nodes will be rolled out, and then the system is called standalone 5G. So when you read a bit about 5G, you'll see non-standalone, which is what's coming now, a hybrid between 4G and 5G, and standalone is 5G with the new core nodes and with the highest possible performance. The markets for all of these sectors are enormous, and the demand is enormous for 5G systems. You can see a few of the figures here. Just to show the industrial automation part, this is current service revenues estimated for 2026 for mobile providers, and on the top you see the extra which would be generated by industrial automation. So it's expected that what's currently a tiny segment, industrial automation, will become a very big segment within a couple of years. And if you look at the areas where automation will be applied, you can see the biggest segment is manufacturing. So that's controlling robots wirelessly, controlling production lines wirelessly and interconnecting them. But the second biggest sector at 16%, almost as big as manufacturing, is energy and utilities. So it's expected that there will be tremendous growth in the use of wireless communications in the energy and utilities sector in the coming years, and within a few years, within 7 years, according to the projections of this slide. It's just to give you an idea of the orders of magnitude. Okay, I mentioned the customers want more bandwidth and more performance. And this slide just shows the different sorts of things coming for consumers, home sensor services, drone delivery within 5 years or within 3 to 4 years, hologram calling, telephone calling within 5 to 6 years, self-driving cars, virtual tactile systems for shopping, virtual reality for cinemas, real-time translation. The size of the bubble shows how much people are willing to pay for these different services. And you can see all of the bubbles are reasonably large, and they're actually all within a couple of years. So people are expecting, these are the expectations of the consumers. They're expecting these technologies and they're willing to pay for them. It just shows the pent-up demand that 5G can address, and how much momentum there is behind the rollout of the network. And for utilities, this means that particularly in cities, 5G will be there, so you might as well use it. And all you need to do is organize that the quality of service is that which you want. And that's foreseen in networks. Oh, that's got slightly corrupted. The performance, so you could compare, for example, the 5G radio network called New Radio with the current LTE 4th generation or with Wi-Fi. And you see here the latency of a Wi-Fi system and the reliability under high load. You see comparison to LTE, the reliability, it's much better, and the latency, it's coming closer to the 1 millisecond. And if you look at 5G, you see the difference in the way it's been designed, highly reliable under load, so it doesn't break down, it doesn't lose the connection, and very low latency, down to milliseconds. Platforms, just to give you an example of what a platform looks like for 5G, what the software architecture is. You've got business support systems at the top is the typical Ericsson architecture for 5G. Then you have the management and orchestration of the communications network. So you orchestrate all the services. Then you have the radio systems. And the radio access is what you see, the antennas and base stations and their connection to, normally to a fiber. There's usually a fiber connected to the base station, which is then taking the communications via fiber to the core network. You can also use radio or microwave and you can in fact use the 5G network for the communications to the rest of the network. But it's often a fiber, and then the transport is the system in the background, the backhaul, which brings the communications messages to the core network, to the servers, distributes them, and connects the calls end to end. Then you have cloud. Increasingly, everything is being put in the cloud and virtualized, including all of the network functionality, and that makes it much more flexible and scalable, so that you get increased capacity when you need it for particular events, Olympics, large sports events. You need to reorganize capacity, and if your network capacity or network capabilities are also organized in a cloud fashion, it's easy to change the capacities and the organization. And then you can also load applications like utility applications in the cloud and run them with the same system, and you have the advantage of security and scalability, and it's all organized in a professional industry-grade manner. And you have the Ericsson cloud infrastructure running that, and network services at the bottom of the diagram. Security, I mentioned, 4G security has never been broken. So you start at the bottom with trusted nodes and products. They're very well defined and considered at global level by all the operators and manufacturers in the standardization. They lead to a trusted network, which gives you trusted operations, and basically you can have trust at the business level in your communications. And that's the advantage of a global standard designed in that way. Device availability for 5G. The first phones were shown in Mobile World Congress just a few weeks ago in Barcelona, but they'll be available on the market in Q4 this year as products. Prices I heard were from, I think, $500 or $600 from some manufacturers, and I know of phones coming on the market for about $1,000 a phone in Q4 as well, that will have more capabilities. So first devices will be on the market later this year. The industry IoT modules will come in 2020, and then much cheaper, massively large-scale produced massive IoT devices where the cost will really come down will be a couple of years later. It will take some time for the market to build up, and it's expected that the prices of the devices will come down very rapidly. And here you see the introduction of the two types of 5G, the non-standalone system, which is the hybrid with 4G, and then the standalone 5G, which has all of the functionality. I mentioned private networks are becoming very popular. Just some examples of what they're being used for. Public safety. There's a private network that AT&T has built in the US for public safety use. Then the Rotterdam port is using a private network which Ericsson built to control everything and manage everything. And power utilities, I actually have a short video which is on YouTube of the Ericsson installation of a private network for Southern Link Wireless in the US. It's based on LTE. It's already up and running. And it might be interesting for you to look at that 5-minute video. Okay, then I mentioned features. If you're using a public network, 5G will anyway be in cities. The network is designed that many users can use it in parallel from an industrial perspective. And what you want is to be sure that your part of the network is working the way you want it to do. And the way that's organized in 5G is to have a new feature called network slicing. And basically the network is sliced up end to end, terminal to terminal, and the quality of service is controlled in each slice. Each slice is separate, and you can set your own quality of service. So you can set priorities. Is latency the priority? Is performance the priority? Which users have priority? Which devices have priority? And it's done by reserving capacities in the network rather than having everybody having the same priority or just one set of priorities for the whole network. So this concept of network slicing is important in the industrial automation context and for use by utilities. It also gives the user, the utility or industrial automation organizer, insight into how the network is performing. So if a node is down or an antenna is down, it's visible to the owner of the slice. And that wouldn't be possible with today's networks, or at least with older networks. In 4G, it can be introduced, but this is a key feature of 5G, which makes it more suitable for this type of industrial automation. And you can see the statistics and the figures on the performance. You can have up to 100 times more connected devices. And this becomes very important if you think of a smart city context, where in 10 years' time you could have people wearing sensors, the rooms have sensors, the lighting is organized according to the sensors and the settings of the people who are in the room, where everything is personalized, heating, etc. And then you have everything running on 5G sensors or similar systems. The number of devices per cubic meter will be rapidly increasing. And that was one of the reasons to enable enormous numbers of devices to be connected per cubic kilometer and meter in 5G. Mobile data volumes, I mentioned, is very important for the operators and the users. The latency is very important for the industrial sector, and the data rates for the mobile operators. Some of the things slices would be used for would be interactive gaming, to give you the lowest latency and to ensure that everybody had a good experience in a gaming organization. For controlling robots, where you want to be sure that the robot does what's expected and that there's no problems with the communications to the robot. Or connected vehicles to take away traffic lights and control the cars individually, which is planned. And again, you need a very high reliability service and dedicated quality of service. So these are all things that slicing is foreseen for. Another example is control of railways. And here you see in one slice, you've got the one slice of a 5G network. You have the public mobile broadband, which is the normal 5G network. And then you have a slice set aside for the railway control. And you could have on high priority driver communication and management systems, medium priority security cameras, and lowest priority the Wi-Fi for the passengers on the train, but all working within the one slice and visible to the railway operator. And that in parallel with a completely separate slice for the normal public 5G. And this gives you an idea of the architecture used. Just to come then to use cases for the power grid for 5G, you've got the current situation on the road to 5G, hybrid systems and the 5G standalone systems from 2023 onwards. Now we have smart metering as a big use case and automation of the grid. We're moving into increasingly more distributed energy resource management and distribution automation, with services being offered in the cloud, with 4G and 5G communications over the wireless sector. And then with full standalone 5G, you can have much more real-time control of edge of grid generation, virtual power plants, real-time load balancing, network slicing, the full range of features. Just in characteristics of the requirements, currently you try to get coverage, so you're connecting lots of new meters that need communications, and you want a robust performance, but not extreme reliability. With the new systems with 4G, you have much lower latency, under 20 milliseconds. You have high throughput with LTE. You have network slicing available, dynamic service orchestration, analytics, etc. And then we're moving towards lower latency and 5 nines reliability. Very high reliability, even more than is provided by the power network in most cases. And you have new radio. This is the high capacity radio system. You have radio access network virtualization, so large parts of the communications are virtualized. You can federate the network slices, not just slice it up, but federate them. And distributed cloud services, and everything supported by AI techniques. So summarizing, utility networks will require very high availability and reliability services, secure communication points, low latency, and end user quality of service control. And these are the requirements that are behind the 5G design: high availability and reliability, low latency, security features, edge processing of data, which can be very useful in the blackout situation, network slicing, and reconfigurable networks using SDN, and with devices and integration of 4G and narrowband IoT systems. So moving on to the final section, a few slides on laboratory testing and field trials. What we typically do in the laboratory, which you can see in the basement here, and you'll be using on Friday morning, is to connect the RTDS or some similar OPAL power network simulator via laptops with dongles, which are sending signals over the air to antennas and a full wireless network, which is live in the basement and running indoors. So these are the normal systems you would see outdoor on the roof, but running at very low power downstairs in the lab in test frequencies that are allocated for use at this precise location at very low power. So it's regulated systems, but you've got the full live power network. And we produce the message streams as if they were in the power network from the simulator, and we drive them over the air to the base station, and then we can look at the latency and the throughput performance. And we typically would be looking at different protocols that could be used and different message streams. Some protocols work very well over radio networks and others don't. In particular, chatting protocols that have loads of acknowledgements or that have bursts of traffic, they don't work very well over radio networks. You get big problems because the protocols in the radio network work against such chatty protocols or bursts. And then you can see the performance, and then you can choose the protocols you want to use for your energy system according to how they're going to perform, and at least you know in advance how they're going to perform. And then we can look at the different message patterns that would be typical of the use case in the power network and see how it runs, and you can see then the reliability, the performance that you get, and what happens under heavy load. And that we've done in several projects, such as in Success, where we've done such networks in the lab, but we also have field trials, but not with live 5G. In some cases, we've been able to use 4G. Otherwise, we used cables and did the simulations on the 5G in the lab. And for our cybersecurity system, I mentioned that we had 3 DSOs from Ireland, Italy, and Romania producing live data, simulated attacks on their network for our power monitoring system at pan-European level. We also used the new meters we've developed, the norm meter, and low-cost PMUs, and deployed them in field trials in the live DSO networks. In Sonio, where we're looking at distributed services in the cloud, we're now setting up trials which are going live in this quarter in 4 countries, including here on the campus, which is one of the trial sites of the project. We also have Ireland. We have CEZ, a distribution operator, a very big one in Romania. And in Estonia, we're using the campus and the Electrolevy grids as trial sites. And in Reserve, the project which was the main organizer of the course, we also have field trials. We have Romania, we have Italy, we have Germany, and we have Ireland in the trials. So we experiment with all of the techniques in live DSO networks with DSOs because we want the real requirements on the networks. And then we do a lot of experiments in the lab. And when possible, it's becoming now possible that we can do outdoor experiments with 5G and test the systems in the field. As the system has been standardized, 5G has been standardized, and production equipment will become available this year. So key messages: expectations are changing regarding the role of energy in society. The reliance on the power supply is rapidly increasing, and I don't see anything that would change that trend. It will produce a trend towards distribution to give more resilience in the system, to distribute the system and rather than have a centralized system. It means increasingly communication is needed. Near real-time communication is needed to control the system. A lot more software will be needed. And the operation of the energy systems is increasingly challenged by security threats and cascading effects of attacks, as well as the increasing complexity of all the systems, which make it difficult to know what's going to happen when something goes wrong. And increasingly you need ICT, and 5G systems and services, I think, will have a very big role to play as a part of the solutions. So I hope you've got some idea why we're working on 5G in the energy sector, why we're working with the DSOs, what 5G will do and when it's coming, when the devices are coming, what sort of capabilities it has, and what's been happening in the last 2 to 3 years in relation to trials in the lab and in field trials of energy systems, where we're looking at specifically the use of 5G for those energy systems. Well, that was my objective with my talk. I hope you've got that overview. There's a lot of slides, a lot of information in a short period of time, but I hope it fits together. Happy to answer any questions now or in the coffee break or via email. Thank you very much.